It's time for another amazing chemistry video with Mr. Stapleton, proudly sponsored by Farmers Union Nice Coffee.
Hi guys, this is the first video in the next topic for Year 12 Chemistry. This is topic 2, which is managing chemical processes. Now I just want to remind you that embedded throughout this presentation you will find links to my YouTube videos, so all you got to do is click on this YouTube play button here, and that will allow you to go directly to a link. Now obviously you need to have downloaded the PowerPoint of this, you can't just do it straight off the videos, but if you're watching this on the video on YouTube, hopefully you'll already be able to see my other videos there as well. And if you do want to see or get the link to my website where you can get the different PowerPoints and some of my other resources from that, just leave a comment below and I'll be happy to send you the information. Alright, so this first topic is going to be all about rates of reaction. So I'm going to be going through collision theory and things that impact on the rate of a reaction. And so hopefully it'll make a bit of sense to you, but as always, if you have any questions, ask me in the comments. I'm more than happy to try and explain more if I need to. So the first thing you need to understand is what activation energy is. Okay, and activation energy is basically the minimum energy required for a reaction to occur. So we've got this guy who's pushing this boulder up a hill here, and the boulder isn't going to start rolling down the hill, alright, until he puts enough energy in to get it to the top. Once he gets it to the top, alright, and he's put the energy in, the reaction will then start all by itself afterwards, okay? So you have to put that minimum energy in, and the energy he requires is the distance between where he is and he needs to overcome that to that height of that hill there. So the basic principle is that in order for particles to react, they must collide with sufficient energy and the correct orientation. Okay, and that minimum energy is the activation energy, as I said. So what we've got here is just got an example of a little video that I've put together in the PowerPoint just to show you some of the things that will impact upon a collision. Okay, so I'm going to play that for you now. And what you can see here is that we've got two particles that are moving together, closer towards each other. They don't have sufficient energy when they collide with each other, so they don't react. Okay, they do have the correct orientation, so they're coming together and they're going to hit each other nicely, but they're not actually got the correct orientation, correct energy or sufficient energy to be able to react. Here in this one, what we've got is two particles here. Now, what's going to happen is these are going to have enough energy to react. Okay, so they're going to be moving fast enough. But because they're not in the correct orientation this time, they don't react. This one here is going to have both the correct orientation and the correct amount of energy, the minimum energy required. So you can see these particles are lined up nicely. Okay, they're going to go at each other with enough energy to be able to actually cause a reaction to occur. And what we're going to see is, bang, we've created new molecules. Okay, so that's basically the principle of the collision theory, that in order for particles to react, they must collide with sufficient energy and the correct orientation. Can't have one without the other. Okay, so what we also need to understand is not only that in order for particles to react, they must have the minimum energy and correct orientation, we also need to understand what type of a reaction it is, so whether it's an endothermic reaction or an endothermic reaction. An endothermic reaction is one where energy enters the system. Okay, so the energy of our products is higher than the energy of our reactants. Whereas in an exothermic reaction, energy exits the system or leaves it, so the energy of our products is lower. So what we have here is a negative enthalpy value, here we have a positive enthalpy value. We'll cover more on enthalpy in later topics, I'm not going to go into it in a great amount of detail here. What I just need you to know in this is that these are called energy profile graphs. Okay, and that the activation energy is the difference between the energy of your reactants and the highest point of your graph, and so that is the energy required for the reaction to occur. Exothermic reactions are normally pretty good because they produce energy. Quite often, once the reaction actually starts, they produce the minimum energy required for the reaction to occur here, and so they're spontaneous and keep going. So if you want to talk about how to calculate the rate of a reaction, there's two ways you can do it. It's either by changing number of moles per unit time or changing concentration per unit time. And if you think about it, really they're kind of related to each other anyway, because your concentration is normally moles per litre. So if you're changing the number of moles you've got in your fixed volume space, you're going to be changing the concentration anyway. If we graph a rate of a reaction, we can tell how fast the rate is going by looking at the slope of the graph. So here we've got a graph showing time along the bottom, and we've got a number of moles on here. This could easily be concentration as well. Okay, and you can see at the beginning, the number of moles is changing really rapidly. So that has a steep slope, which tells us that therefore that's a fast rate of reaction, which makes sense. As the time goes on, you can see the number of moles that changes is starting to decrease. What that means is that the rate is starting to slow down, and once we get to actually a horizontal slope there, alright, that means that the reaction has actually stopped. Alright, so if you remember that the slope of a graph is equal to the rate, the steeper the slope, the faster the rate, you'll be easily able to remember things. So, some of the things we're going to look at for factors that affect the rate of a reaction. The first one we're going to look at is nature of the reactants. Okay, so here what we've got is we've got some chemicals which are already in solution. So basically what happens in a chemical reaction is you have bond breaking and then bond making. Okay, so you have to break the bonds in the reactants, and then you have to form the bonds in the products. If you've already got the bonds broken, alright, so in solution here where we've got ions, we've already separated the anion and the cation, we've broken the bonds there, so all we've got to do is do bond forming, and what we end up with is a much faster reaction. Whereas something like this, combustion, what you've got to do is you've got to break down the bonds within your fuel, and you've got to form new bonds for your carbon dioxide and your water as a product. So generally where you have to break bonds and then make them, they're slower than ones where you have to just make the new bonds for the products. Next one is concentration. It makes sense, and I always liken this and explain to people about thinking of Dodgem cars. If you ever driven Dodgem cars, obviously they're a lot of fun. So if you think about it, if you've got two Dodgem cars within a rink, what you're going to find is they're going to collide into each other not very often. Okay, even if they're going really, really fast, they'll still only collide into each other every so often. If you chuck 20 cars in there though, okay, those cars, there's going to be a lot more collisions occurring between those cars because you've got so many more in that vicinity. You haven't changed the area of it, but you've just increased the number in there. So if you increase the number of moles in a given volume that doesn't change, you're going to increase the number of successful collisions. Because you've got more successful collisions occurring, there's going to be a greater rate of reaction per unit time, and that's going to increase your rate. So the key thing to work out here is that the rate is proportional to the concentration. So if you double the rate, if you double the concentration, you'll double the rate, which makes sense. Here in this graph, you can see what we've got is we've got our reactants, which are initially very high in concentration. As they start to react to form the green products, the concentration decreases and the rate slows down, so our slope is lower. And our products, initially the rate of formation is fast. As the concentration of the reactant decreases, the formation of the products decreases until we get to a point where the concentration of both of them is constant, and that's where the reaction has stopped. Temperature is another one that can really affect the rate of a reaction, and you can obviously think about this very commonly. A fridge, for example. A fridge slows down the rate of decomposition of food. That's the reason we have them. So when you put food in a fridge, the particles react at a much slower rate, which means that they go off, the food goes off much slower. Conversely, if you think about cooking food, for example, food gets cooked a lot faster the higher the temperature. So what happens is that you have the particles which are moving around. When you supply temperature, or when you increase the temperature, you're supplying energy to the particles, which makes them move faster. Not only do they move faster, which means more collisions, but you also have more particles, therefore, which have the minimum energy required to react. And we can show that in this graph. So here, this is our normal standard temperature, the blue graph. Okay, this is like a bell curve distribution, and only the particles to the right of the red line, these ones down here, have enough energy to be able to react. If you increase the temperature though, more particles have higher kinetic energy because they're moving faster, so more of them have the energy required for a reaction to occur. So there's a lot more particles over this side which can react. Same thing, if you decrease the temperature here, much less particles, good English, fewer particles have energy greater than or equal to the activation energy, and so the rate of reaction is slower. The general rule is that a 10-degree rise in temperature doubles the rate of a reaction, so a 20-degree rise would quadruple the rate, A 30 degrees rise would increase the rate by 8 times, a 40 degree rise by 16, so it doubles every time. Okay? So the key thing about temperature is that it supplies energy to the particles. It means they move faster, so more particles have energy greater than the activation energy, and because they're moving faster, there's more successful collisions per unit of time, so there's an increased rate of a reaction. Next one is size of the particles, or it's called state of subdivision, all fancy words for surface area. Okay, the greater the surface area, the more particles that there are that can come into contact with each other, so there's more collisions that are occurring, so hence there are more frequent collisions that are successful, which increases the rate of a reaction again per unit of time. So you can see here, if we've only got these 5 particles down here, we're going to have some collisions occurring, okay, but there's not going to be as many collisions occurring as where we've got all the particles that are smaller. So we haven't changed what the particles are, we've just broken them up into smaller amounts. So this can be as simple as in a reaction with metal, right? If you want to dissolve sodium in water, it will dissolve a lot faster if instead of just doing one big cube, if you cut it into lots of tiny ones and put it in the water, it will dissolve faster. Another really good example of dissolving aspirin. Alright, if you want to dissolve aspirin, you crush up a tablet, it dissolves a lot faster than it does when it's a big tablet, because there's more particles able to dissolve and there's a faster rate of reaction. So, if you can remember for surface area, the more particles you have, the more collisions there are, which means there's going to be more successful collisions per unit of time. Next one is presence of light, or what we call photochemical reactions. So photochemical reactions are chemical reactions that rely upon the presence of light. So light is very similar to temperature in that it supplies energy to the particles, which means they move faster, which means that they collide more often, and when they do collide, they have the energy greater than or equal to the activation energy. Alright, I've got this picture here because photography, and not digital photography, but old school film photography, relies upon light activating the surface of the film here. It's normally like a silver substance, and as the light reacts with it, the silver reacts in the light, and it forms an image on the negative. Other things are photosynthesis obviously requires sunlight to react as well, and so if you have more sunlight, the reaction occurs faster. Final one is a catalyst. Now, a catalyst, a good year 11 definition of a catalyst is something that speeds up a reaction. For year 12, what you need to be able to explain a catalyst is something that provides an alternative reaction pathway with a lower activation energy, and it's something that also helps to line reactants up with the correct orientation. Now, it doesn't always do both things. Okay, so there are some catalysts that don't line reactants up with the correct orientation, but pretty much all catalysts reduce the activation energy. So what that means, if we go back to our energy profile graph here, remember the energy required for this reaction to occur is the energy between the reactants and the top of the graph here. So we've got to supply all this energy. If we use a catalyst, we have an alternative energy pathway, and that means we reduce this activation energy. So we need less energy in order for it to react. We can show this as well with an energy distribution graph. Okay, with an energy distribution graph, you can see this is the original activation energy. When we bring it down this way, okay, we lower the activation energy, there are more particles that are able to react. So that alternative energy pathway means that you have more particles with energy greater than or equal to the activation energy, which means you have more successful collisions per unit time. Now, what also happens sometimes, and so catalytic converters are a good example of this, is where they line up the particles with the correct orientation, and so the particles stick to the surface of the catalytic converter in such a way that when other particles come into contact, they will actually react with them more readily. So that's the other thing a catalyst can do. The great thing about catalysts is that they are not used up in a reaction. So here we've got, somebody spends a lot of time setting up all these dominoes. Okay, this little red ball, right, is just going to initiate the reaction. So it's going to start it. It's going to provide the energy required for the reaction, and it's going to but not be used up. All right, so we can reuse that ball to start other reactions of the dominoes as well. So some examples are in the body. We've got enzymes. Enzymes are natural catalysts. Okay, Okay, and we're going to talk about those in just a second. But the other things we can use them, as I said, are in cars. We generally use platinum or palladium. Ozone destruction involves chlorine atoms which are released from chlorofluorocarbons. When you make esters later on in the organic topic, you're going to use probably sulfuric acid or sodium hydroxide as a catalyst, which increases the rate of a reaction much faster as well. But if we talk about enzymes as catalysts, enzymes, and this is a little bit of biology, so those of you doing biology will get a little bit more insight into this as well. We're not going to go into much more depth, other than to explain that it's a little bit like a lock and a key. Okay, if you want to get into a house through a door, all right, you've got to be able to have the key specific for that lock. Similar sort of thing within the body. We have active sites which are in enzymes, okay? And what happens is those enzymes allow what we call substrates or molecules within inside our body to actually react much faster than they would normally. Now this is really, really important because if there's a lot of chemical reactions inside the body which if they happen slowly, okay, we wouldn't be able to function the way we're supposed to. So we've got our enzyme here. Here's our active site. We have our two molecules that are wanting to react. Now, if you just want to wait for them to react normally, they'll be floating around and we have to wait for them to collide with the correct orientation and minimum energy. Instead though, what the enzyme does is it kind of locks them in place, okay, so you can see we get them locked into place here. It causes them to react and we get our product forming over here. Now that happens much faster than it would normally within the body. Alright, so what we've done in this first one is we've gone through the collision theory. We've talked about how in order for particles to react, they must collide with minimum energy or activation energy and the correct orientation. We've looked at all the 6 factors that influence the rate of a reaction, and we've looked at how we can represent that with energy profile graphs and energy distribution graphs. So I suggest you make sure you have this really locked down before you move on, because you need to have a real good understanding of collision theory and what affects the rate of a reaction if you're going to go on and do well in the rest of this topic when we look at equilibrium and industrial processes. Alright, thanks for watching guys, really appreciate you taking the time to have a look at this, and as always if you've got any questions just ask. Thanks.